A satellite is situated in the Earth at an altitude 150 kilometers above its surface, where the free fall acceleration g is 9.4 meters per second squared. See the figure below. The Earth's radius is 6,400 kilometers. A. What is the orbital speed and period of the satellite? B. If the satellite is to escape the gravitational field of the Earth, what speed will it have? So this is the question that we're going to consider. We have got this data of this satellite that is orbiting, that is orbiting the Earth at this altitude, where this is the radius of the Earth, this is the gravitational field strength, which is 9.4 as the question demands. So now, we are trying to find the orbital speed of the satellite, the period of the satellite, and the escape velocity. Okay, so this is the information that we have. Now, we know that this is orbiting. It is orbiting the Earth. And we know that as it is orbiting, it is undergoing centripetal force. And again, the force of attraction between this and this is the gravitational force. So we have Fc, centripetal force, which is mv squared, okay, or let's say just mv squared over r. So we can call this as equation 1, as it is orbiting. Now, there is a force of attraction between the two, between the mass of the Earth and this mass of the satellite, and that is Fg. So this is the Fg is given by G, the gravitational constant, then m over r squared. So this one we can call it as equation number 2. So since these forces must balance at this orbits the Earth, equation 1 or Fc is equal to Fg. So 1 is equal to 2. So we have mv squared over r is equal to g m over r squared. This and this can go, then also this and this can also go. So we're going to have v squared is equal to g m over r. But since it is orbiting at an altitude, which is this one, this r is equal to re plus h, radius of the Earth plus h. So our v squared is equal to gm over re plus h. So this is, let us take note of this equation. And let me just erase this. So this one, so our v will be equal to square root of gm over re, radius of the Earth, plus this one. But at the same time, we know that, okay, so since the force of gravity is influenced or is represented by mg, and the force of attraction between the two bodies, the force of attraction, it is this same, this one, m over r squared. So this one, mg again, it is the force of attraction, like this one. Weight must be equal to Fg, and weight is equal to mg. So here we have mg is equal to gm m over r squared. But this one and this one can go, and and we're going to have G is equal to G M over R squared. So Gm is equal to G R squared. But at an altitude, at an altitude of h, so R is equal to Re plus h. So here we have G radius of the earth plus h squared. So if we put this one into this, we are going to have V, but this and this equal, so we can cancel this and a square here. And what we are going to have is, so this is the expression that we are going to get for the velocity of the satellite. If we put in the values for the values that we had, we are going to get, if we put this one 9.8, then the radius of the earth plus radius of plus the altitude here, we are going to get 8.1 times 10 to the power 3 meters per second. This is an approximation of what we're going to get when we plug in the values for this. In this video, I just wanted to let you know about the overall information that we need to know here. For period, the speed of an object that is orbiting a circle or any circular path is given by the perimeter or the distance around the circle, which is 2 pi r over t. So from this, we can make t the subject by simply cross multiplying, and we're going to have 2bt. Since we want t, we can divide by b, even here by b. So that this and this will go, and we're going to have t. But it was found that v to square root of gm, which is the mass of the earth, over r. So if we put this in this, we're going to have 2 pi r over. So this one can be also like this, 2 pi r times square root of r here, when this one comes up, because this one is the same as square root of gme over square root of r. This one, so it can be written as follows also, so that we have square root of gme. So from this, it is the same as 2 pi r then times r power half. But since the bases are common, we can add the powers. So we have this is raised to the power 1, so it's 1 plus 1 over 2. So we have 2 here, we have 2 plus this into this 1. So we are going to have 3 over 2 on top here. So here, square root of gme. 2 pi r 3 over 2 over square root of gme. So this one we're going to get, so this one we're going to have 2 pi, then this one, it is the square root of r to the third power over square root of gme, which can also be written as 2 pi square root of r to the power 3 over gme as the period. So now coming back to escape velocity. Escape velocity is the minimum velocity that is projected to an object, or that is given to an object so that it can escape the Earth's gravitational field. That is escape velocity. So part C. Escape velocity. So this one is found by relating to kinetic or to mechanical energy. So we have kinetic energy initial plus potential energy initial must be equal to kinetic energy final plus PE or potential energy final. This one we're going to have MS and MS can go. So this and this can go, and we're going to have VE squared over 2 is equal to GME over R. So this one we can multiply through by 2 to get rid of a 2 here. So we're going to have escape velocity. So this one, we know from the relation that we just had to say Gm is equal to G, then R E plus H squared. So putting this one into this, we're going to have V, and this one, we're going to have VE squared is equal to, or just V, if we introduce the square here, and also the square root here, the square root here and here, we're going to have square root of 2G RE plus H. So this is the expression for escape velocity. So if you plug in the given values for G, the radius of the earth and the altitude, and punch on a calculator, what we're going to find is the escape velocity. Thank you so much, Cosme.